Now we have arrived at the discussion of the t-distribution. So a little bit of background on the t-distribution. It was developed by William Gossett, who was writing under the name student. And basically what he was trying to do was figure out ways to do quality control between batches of beer being made at the Guinness Brewery. So he was looking at small scale materials and different temperature experiments. Fun fact, this was a picture I actually took at the St. James Brewery. So with the t-distribution, as sample size lowercase n gets larger, the t-curves are going to be getting closer and closer to one another. And eventually it gets closer to the z-curve. When you're working with a t-curve, you need to specify the one that you're using. So the way you would do that is by looking at a t-curve corresponding to a sample size of n. For example, n equals 15. But it's actually more common to be using degrees of freedom because degrees of freedom will be n minus 1. And so it helps us to get some more information to go into that computation of standard deviation. So with the t-distribution, the bad news is when we take our sample mean minus our population mean and divide it by my standard error of the sample mean, this is no longer a z-value. But the good news is we know what this value is. It's a t random variable. So in the case when you don't know the sample sigma, the population sigma, you're going to use the sample standard deviation, but when you do that, you are now looking at a t-distribution. So if we start with our standard normal z with a mean of 0 and a standard deviation of 1, this is what we would see. So if I were to look at the t-distribution for a sample of 20, it's a little bit flatter, the tails are farther out, and the mode is not quite so tall. And then if I decrease my sample size even more, my curve becomes even flatter. So the thing that we want to keep in mind is that the shape of the t-curve is going to completely depend on our sample size. Now, in this discussion, I showed you what happens to my t-curve as I decrease my sample size. But remember, as my sample size approaches infinity, the t-curve is going to resemble the standard normal z-curve. So some properties of t-curves. So we've got a family of these bell-shaped distributions. So they're going to be symmetric about 0, just like our z-curve. The total area under the curve is going to be 1, just like the z-curve. The area on each side, once again, is going to be split evenly. But the big difference is that it's going to have fatter tails than your z-curve. So when I'm looking at the t-distribution, the degrees of freedom is going to be our number of observations minus 1. So to see why this happens, suppose you have 3 numbers with the mean of 10. So my first value is 8, my second one is 9. So since the mean is 10, that means the total of my 3 numbers must equal 30. And then I already know that I've got 8 and 9, and 8 plus 9 is 13. So therefore, my last value has to be 13. So in this case, if I know the mean, I only need to know 2 of the 3 values to figure out what's going on with my data. So if I look at the t-distribution table, once again, I said earlier, as you approach infinity, if you have more than 100 degrees of freedom, the standard normal z value is going to provide you a good approximation of your value. But basically the way you would use the t-distribution table is you locate your number of degrees of freedom on the far left side, and then you move to the right until you get to your alpha value.